Hello everyone, my name is Delifina Martinez Pandiani. I'm currently a doctoral candidate at the University of Bologna in computer science. I work with the Semantic Technology Laboratory under Professor Rasuti, and I will be talking about my dissertation work, which is centered on the automatic modeling and interpretable detection of abstract concepts from cultural images. Abstract concepts such as freedom, safety, violence, comfort are a powerful tool for indexing and managing visual data. This is because they bridge cultural meanings through what William Barthes called the connotation of an image, but at the same time, this is a task of high technical and social-cultural complexity. This comes from the fact that abstract concepts can be very culturally nuanced and subjective, and therefore there's a high entropy in terms of the kinds of visual data that may evoke the same abstract concept. The purpose of my research is to translate cognitive science ideas and theories about how the human brain represents abstract concepts into a software architecture that can learn how abstract concepts may be evoked by visual data. The technical objective is to develop a hybrid method to test different subsymbolic and symbolic methods for understanding how automatic visual evocation of abstract concepts can move forward, with a focus not only on performance but also on explainability. The fact that this is a social cultural task with high complexity centers the idea of interpretability, explainability, because the harm of bias being replicated through these types of models is higher. So the enhanced contextualization and explainability of models that attempt to visually connect abstract concepts with visual data is of very high importance because it can ease model behavior explanation. So knowing why a model may have detected violence or freedom or oppression in an image is just as important as the accuracy. So the hypothesis that we are testing is that there are visual features that can act as proxies for the evocation of abstract concepts that would mirror the cognitive science theory of acquired embodiment, of relationality, multiple representation view. There's the idea that we can translate these into a system that automatically models the abstract concepts based on these patterns, and then can use them for the interpretable detection of abstract concepts from visual data. At the core is that no explicit definition of abstract concept is needed, but instead common sense descriptions can be derived from the observations of their usage. So by looking at what images may be tagged with these concepts, we may be able to identify patterns. In order to do this, we have to first understand how humans and machines are currently understanding visual data and how high-level semantic visual tasks may mirror each other in humans and in computer vision. So overall, in this state-of-the-art survey that I did, we found that there was an increasing interest in automating high-level computer vision tasks, including very abstract concepts being automatically evoked from purely visual data, such as the political affiliation of people, the personality traits of people, intimacy prediction, beauty prediction, rhetorical analyses of images, which are all tasks and concepts that, when it comes to the human visual understanding, have always been put at the top of the semantic pyramid, in which the subjective variability is very high and the cognitive complexity is very high as well. This means that for the computer vision tasks, the data is very variable and usually quite difficult to come across. In order to approach this, we have followed a method of using multimodal frames as the way to model these concepts based on the extraction, analysis, and integration of both sensory perceptual and distributional linguistic data, and integrating it into a scalable ontology-based knowledge graph. This allows for explicit reasoning and explicit semantics, Specifically, we developed the Musco ontology, which is an ontology to describe abstract concepts as multimodal frames, and combined it with the coded visions ontology, which I have also developed, which situates ground truths of the computer vision pipelines into the context within which they were giving that meaning. That means that images can be tagged with differing or even contradictory concepts by different humans, and thus hard-coding the context within which these annotations are assigned is very important to later develop downstream interpretable systems. So the Musco knowledge graph contains these kinds of information. And then we created the R-struct dataset, and we trained baseline models to provide to the community for the task, which hasn't been really formalized before. For this, we used different datasets that are available, but that have not been cleaned or generally curated for abstract concepts annotations. So the R-struct dataset contains photographic images, historical images, paintings and advertisements coming from, for example, the Tate Gallery in the UK, as well as Wikipedia, Artpedia and the WikiArt. And we have used the idea of evoked clusters in order to assign the abstract concepts tagged by them. The very little research in computer vision that attempts to do a similar task to the one that we're interested in also uses this idea of evoked clusters. So for example, the concepts danger, peril, and risk tend to co-occur. So they are one cluster, which in our case we call danger. Here we see 4 examples of cultural images tagged with the concept of danger, and the visual variability is very evident in the example. We also released the R-struct dataset, a version of the R-struct dataset that is balanced, because before, in the unbalanced version, a great majority of the images are tagged with the concept of comfort. In order to exploit our ideas and the R-struct dataset, we did an experiment to try to understand how the baselines that were fine-tuned, that were trained by using the VGG convolutional neural network and ResNet, fine-tuning them on R-struct, may be collapsing meanings. They may be collapsing abstract concepts within their architecture, and what kinds of visions of the world are being collapsed. To do this, we focused on activation maximization, and we developed a new method that combines the activation maximization, specifically feature visualization, with stable diffusion. This means that for the neurons in the second to last layer that are responsible for classifying a specific, for determining the probability that an image is a specific class of the abstract concepts, we were able to get the activation maximization images, and by normally regularizing them, we can see the middle image here, they were completely unintelligible, while for concrete classes many times they are much more intelligible, like the Google Deep Dream images. So by using stable diffusion, but without linguistic input, we were able to get more human intelligible images that actually resembled human-made artworks, which makes sense because the network was fine-tuned on an artwork and cultural image dataset. So by combining these techniques, we were able to develop a method that allows us to try to investigate and explore the kinds of cultural meanings that are getting collapsed in deep models. Another approach that we're testing is to use informed learning with prior knowledge. So we talked about the knowledge graph, the ontology-based knowledge graph that is holding the information about abstract concepts as multimodal frames. So that inspired the idea of extracting perceptual semantics from images at a more concrete level. So for example, object detection, action detection, color palette detection, and extraction, using these perceptual semantics in combination with ontology-based knowledge graphs in order to classify images based on abstract concepts and attempt to identify what specific features at this more concrete level with specific concepts may be contributing to a successful classification. Some of the results are quite interesting. For example, for the fine-tuned convolutional neural networks that were fine-tuned on the R-Struct dataset, we found with the GradCam method that the network was able to learn certain common sense features that may be bridges between visual data and abstract concepts. For example, on the right, one can see that the comfort class, the part of the image of this important and famous painting, Triumph of the Virtues over the Vices, the part of the image that was most relevant to comfort classification was the top right, in which there's a person laying down in a seemingly comfortable position. Whereas for freedom, for example, the flying angels and a raised sword were the most important ones. And this indicates that the R-Struct dataset may include specific depictions, for example, with freedom, that are connected to angels and swords. The performance of these baselines is quite low compared to computer vision tasks that are around concrete labels, but these results are in line with the state of the art for these kinds of high-level visual understanding tasks, and they show a certain potential for improvement. In general, the conclusions that can be made so far are that abstract concepts are a good case study for the constant and increasing need for explainability in computer vision systems, especially as the field moves more towards high-level abstract reasoning tasks that are culturally nuanced. The explainability is becoming crucial because in subsymbolic methods, concepts get dissolved in complex and very hard to decipher ways. This leads us to think of hybrid methods and neurosymbolic methods as a prominent avenue of research that allows us to strike a balance between the representational capacity and the explainability of systems and models. And overall, it points us towards the idea of interdisciplinary research in which concrete representations of cultural knowledge can be learned and explored and understood by the combination of artificial and organic agents. Thank you for listening. If you have any questions about my research, please reach out to me.